In episode 105, titled Regularizing Deep Models, Dropout, Batch Norm, Early Stopping, Schedulers, we focus on how to prevent two common deep learning failures: overfitting, where the model learns the training data too well and generalizes poorly, and instability, where training becomes slow, oscillatory, or divergent. Deep networks have the capacity to learn rich representations, but that same capacity makes them prone to memorizing noise when data is limited or when training is allowed to run unchecked. Regularization in deep learning is therefore not a single trick, but a set of controls that shape how the model learns and how it behaves under iterative optimization. Some controls reduce the model's tendency to rely too heavily on specific internal pathways, while others stabilize signal flow so gradients remain usable. The exam expects you to recognize what each technique does and how it fits into a disciplined training loop. The purpose of this episode is to help you choose these controls intentionally rather than piling them on blindly and hoping they work. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Dropout is a regularization technique that randomly silences neurons during training, meaning certain activations are set to 0 with a specified probability. By forcing the network to learn while parts of its internal feature detectors are temporarily missing, Dropout discourages co-adaptation, where groups of neurons rely on each other in fragile ways that only work on the training set. Conceptually, Dropout makes the network behave like an ensemble of many smaller subnetworks that share weights, because each training step uses a slightly different subset of active units. This often improves generalization because the model learns redundant, distributed representations rather than brittle, highly specific ones. Dropout also reduces the chance that a small set of neurons becomes a single point of failure for prediction. The key is that dropout is applied during training, and inference uses the full network with appropriately scaled activations so predictions remain stable. Understanding dropout as controlled noise injected into the network's internal features helps you see why it can resist overfitting. Batch normalization, often shortened to batch norm, is a technique that stabilizes activations by normalizing intermediate layer outputs during training, which can speed learning and improve stability. By keeping activations within a more consistent range, batch norm reduces the risk that signals drift into extreme regions that cause saturation or unstable gradients. This can make training less sensitive to initialization and feature scaling because the network's internal distributions are actively controlled as training proceeds. Batch norm also often allows higher learning rates without divergence, which can speed convergence. In practice, it can act like a form of regularization as well, because the normalization depends on batch statistics, introducing a small amount of noise similar in spirit to dropout. The most important point is that batch norm is not simply a pre-processing step. It is part of the network's computation graph and affects how learning unfolds. When you think of batch norm as keeping internal signals well scaled, the stability benefits become easy to explain. Early stopping is a training control that halts training when validation performance stops improving, protecting you from the point where the model begins to fit noise rather than signal. Because deep models can continue to reduce training loss long after they have extracted generalizable patterns, you need an external signal to decide when to stop. Validation performance provides that signal because it measures how well the model generalizes to unseen data under the same distribution assumptions. Early stopping watches validation loss or a chosen metric and stops training after performance fails to improve for a defined patience window. This converts training into a disciplined process where you keep the model at its best validation state rather than at the end of a long run. Early stopping is especially valuable when you cannot perfectly predict how many epochs are appropriate for a given dataset and architecture. The key exam-level lesson is that early stopping is a guardrail against overfitting, not a shortcut to avoid evaluation discipline. Learning rate schedulers refine step sizes as training progresses, which helps balance fast early learning with stable convergence later. Early in training, you often want larger steps to make rapid progress toward a good region of parameter space. Later in training, you often want smaller steps so the model can settle into a better solution without bouncing around or overshooting. A scheduler implements this by changing the learning rate over time according to a rule, such as reducing it after a plateau in validation performance or following a predefined decay pattern. This helps training reach better minima by reducing the optimizer's step size as it approaches a solution. Schedulers are not about making the model more complex, but about making the optimization process more efficient and stable. In many real workflows, a sensible scheduler can be the difference between a model that stalls at mediocre performance and one that refines into a stronger generalization state. The exam expects you to recognize schedulers as an optimization control that supports convergence, not as a separate model feature. Dropout can slow convergence because the network is effectively learning under noise, and noise makes the optimization problem harder in the short term. When you randomly silence neurons, the network cannot rely on any single pathway consistently, so it must learn representations that work across many partial subnetworks. That robustness often improves generalization, but it can require more training steps to reach the same training loss. This is why you can see training loss fall more slowly under dropout, even when validation performance improves, which can confuse teams that watch training curves too narrowly. The practical mindset is that dropout is not supposed to maximize training fit quickly. It is supposed to prevent the model from becoming overconfident in fragile internal features. When you interpret dropout through that lens, slower convergence becomes an expected trade rather than a sign of failure. The discipline is to evaluate dropout by validation outcomes, not by training speed alone. Batch norm often reduces sensitivity to initialization and scaling, which is valuable because it makes training more repeatable and less dependent on getting the starting conditions perfect. Without normalization, small differences in initialization or input scale can cause early activations to saturate or blow up, leading to vanishing or exploding gradients and inconsistent results across runs. Batch norm helps keep intermediate signals in a stable range, which supports consistent gradient flow and allows the optimizer to operate in a more predictable regime. This can reduce the need for extremely careful learning rate selection, though learning rate still matters. Batch norm can also make deeper networks trainable where they might otherwise be fragile, which expands the range of architectures that can be used reliably. It is not a cure for all training problems, but it is a practical stability tool that often improves training dynamics. From an exam perspective, remembering that batch norm stabilizes activations and speeds training is usually the intended takeaway. Choosing regularizers should be driven by data size and by signs of overfitting because the same network can behave very differently depending on how much representative data you have. When data is limited, the model's capacity is large relative to evidence, so overfitting risk is high and regularization becomes more important. When data is abundant and the task is complex, the model may benefit more from optimization controls like schedulers and batch norm to train efficiently, while dropout may or may not be needed depending on observed generalization gaps. Overfitting signs include training loss improving while validation loss worsens, validation metrics plateauing while training metrics continue to climb, and unstable performance across folds or retraining runs. Stability issues include oscillating loss curves, sudden divergence, or extreme sensitivity to learning rate, which suggest optimization controls rather than pure regularization might be needed. The exam expects you to choose techniques based on these symptoms rather than applying them by rote. The professional habit is to treat regularizers as responses to observed behavior, not as mandatory decorations. It is critical to avoid applying early stopping based on test set performance information, because that turns the test set into a tuning signal and destroys its role as an unbiased final estimate. If you keep checking test performance during training and stop when it looks best, you are overfitting the entire training process to the test set. The clean workflow is to use a validation set for early stopping, tune hyperparameters based on validation behavior, and then evaluate once on the untouched test set after decisions are finalized. This separation protects the credibility of reported performance and prevents optimistic bias. The temptation to peek at the test set is strong because it feels like just one more check, but it quietly contaminates your final estimate. In governance terms, the test set is a protected asset, and early stopping must not consume it. Remembering this boundary is a core exam competency because it reflects disciplined evaluation practice. Monitoring training and validation curves is the practical way to decide whether regularization and optimization controls are helping. If training loss decreases smoothly while validation loss decreases and then flattens, you might be approaching the point where early stopping will preserve the best generalization. If training loss decreases but validation loss begins rising, you are seeing overfitting and may need stronger regularization or earlier stopping. If both training and validation losses oscillate or spike, you may be dealing with an unstable learning rate or gradient issues that require a scheduler adjustment, batch norm, or different optimizer settings. Plateaus can indicate that learning rate is too low or that the model has reached its current capacity, and a scheduler might help unlock further progress. Curves also help you compare configurations fairly because they show whether improvements are robust or just noise. Treating curves as diagnostics keeps training grounded in evidence and prevents you from mistaking activity for progress. Combining techniques requires caution because too many controls can complicate diagnosis when training behaves poorly. Dropout, batch norm, schedulers, and early stopping can all interact, and if you change multiple things at once, you may not know which change caused an improvement or a regression. In some architectures, dropout and batch norm together can produce unexpected behavior because both introduce noise in different ways, and their combined effect can require retuning learning rates and schedules. Schedulers and early stopping also interact because a scheduler that reduces learning rate after a plateau might delay the point at which early stopping triggers, which can be good or bad depending on the problem. The disciplined approach is to introduce controls incrementally, observe their effects, and keep records so you can reproduce results. This is not an argument against combining tools, but an argument for combining them intentionally. In deep learning, complexity is easy to accumulate and hard to debug, so restraint is a virtue. Documentation of chosen settings is essential, so training and inference remain consistent and testable across retraining cycles. Dropout must be recorded because it changes training dynamics and because inference uses a different behavior, meaning you must ensure the correct mode is used at the right time. Batch norm introduces parameters and running statistics that must be handled consistently, or inference behavior can drift unexpectedly. Early stopping criteria, such as patience and the metric used, should be documented because they determine which model checkpoint becomes the deployed model. Scheduler rules and learning rate settings should also be recorded because they affect convergence and final model quality, and they can be difficult to reconstruct after the fact. Without documentation, results become irreproducible and governance becomes fragile, especially when multiple people train models across time. Documentation turns regularization choices into controlled engineering decisions rather than informal tweaks. This aligns with professional model management because it preserves intent and supports auditability. The anchor memory for episode 105 is that dropout resists overfit, batch norm stabilizes, and early stopping protects. Dropout resists overfitting by preventing co-adaptation and encouraging robust representations. Batch norm stabilizes training by controlling activation scale and supporting consistent gradient flow. Early stopping protects generalization by ending training when validation indicates that further training would fit noise. Learning rate schedulers complement these by refining optimization steps over time, helping the model settle into better solutions. This anchor gives you a quick mapping from tool to purpose, which is what exam questions often probe. It also helps you avoid using tools for the wrong job, such as expecting dropout to fix a too high learning rate or expecting a scheduler to fix data leakage. When you remember the purpose of each tool, you can choose and explain them cleanly. To conclude episode 105, titled Regularizing Deep Models, Dropout, Batch Norm, Early Stopping, Schedulers, name one symptom and one regularization response so you can act decisively. If you see training loss continuing to drop while validation loss starts rising, that symptom indicates overfitting, and a strong response is to apply early stopping based on validation performance and consider adding dropout to reduce co-adaptation. If you see loss oscillating or diverging early in training, that symptom indicates instability, and a strong response is to use batch norm to stabilize activations and to adjust the learning rate or scheduler to reduce step size when needed. The key is to match the response to the observed pattern rather than piling on every control at once. When you can name a symptom and a targeted response, you demonstrate that you understand regularization as a set of purposeful controls for generalization and stability. This is exactly the practical reasoning the exam is designed to reward. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.